Welcome back, everyone. This is part 4, and it's called Transformers, Deeper Understanding Over Longer Texts. So I'm guessing some of you guys are like, are we there yet? We worked all the way up through a fairly complex model of reading that neural networks helped us out with a lot. And then in the last video, we looked at how you can kind of take your reading architecture and attach an ability to sort of predict the next token one at a time and feed it back into your reader architecture. And then you've got writing too all of a sudden. So kind of feels like we've arrived, right? And I think in a lot of ways, it was a major step to get that far, but some more big stuff had to happen to get us all the way to the LLMs that we're seeing today. And one of those things was this concept of a transformer, which it just sounds cool, and there's a fair amount of hype about it and stuff, but it's merited. It was a really big increase in the capability of what neural network models can do. So I'm just going to try to kind of tell the story for how transformers came to be and what they do. So in let's just say roughly 2016 to 2017, researchers were trying to make translation systems work better over longer texts. And by this point in the video series, you know enough to kind of understand how a translation model worked, at least at the time. So translation models, and a lot of them still work this way, but LLMs are kind of changing that. But the way they worked was they had essentially our familiar reading architecture that we've been covering so much. So you'd have this side called the encoder or the reader, and you'd pass your source text through that. This blue box could have been an R and N. And then once you'd read the source text, you had a vector of understanding. Well, you'd pass that all the way over to a similar architecture called the decoder or the writer. And that would sort of seed the first prediction to predict the first word for the translation, which would then get fed into a reader type architecture that's on the writer side. And so it was kind of the architecture we've been looking at, except you had a side of it for each side of the translation, one for the reading the source document and one for writing the translation in the target language, and the information was passed via this final understanding, which was once again a vector of decimal numbers. So this worked well, but imagine if somebody sat you down and they said, okay, I want you to read this entire Wikipedia article, and let's say it's a big one, and then translate it to some language that you know. That's a big challenge if you don't have an eidetic memory. I mean, you can read the whole article and you'll have learned stuff and you'll have some sort of vector of understanding of some sort in your mind that captures what you just read, but it's not nearly enough information to provide sort of a, verbatim translation into another language. So translation systems were struggling over longer texts, and that was a problem that researchers were working on. And so this is going to be very conceptual, but I hope you find it useful. Think about how a human would translate documents. You'd probably read the whole source document or at least part of it, and then you'd start doing your translation. But at various points, you're going to have to go back and look at the source document and pay attention. That's a key word in this whole concept, but pay attention to certain parts in the source document, the parts that are most important for you to select the next token in your translated document. I mean, that's how a human would do it, right? They'd be cross-referencing. As you write the translation, you need to keep sort of recontextualizing, rereading parts of the source document to help you generate the next best part of your translation. And so this concept of paying attention, researchers were working on getting neural networks to do that too. So here's my very conceptual diagram of what they were working on. So in this case, we're translating, I've got a lovely bunch of coconuts to Spanish. And so the decoder, note that I've got this flipped from the way it was on the last slide. So this is the decoder. This is the writer that's writing stuff in Spanish. And the decoder would kind of say, okay, I need to pick another token. My current translation is this. And Mr. encoder slash reader of the source document, I want you to tell me which parts of the source document I most need to pay attention to when selecting my next token. And so this kind of gave the machine the same ability that a human would have, where you would be able to go back and sort of reference the source document while you were generating the translation. And it wasn't that you had to go back and reread the whole source document each time. When you went back to look at the source document, you would just pay attention to the relevant parts. And the neural network, the encoder, would help you pay attention to the right parts to select your next token, Racimo. And then once that token was selected, then the decoder, the writer, would pump it through its own reader module to update its current understanding of what it's written so far. And that process would proceed consecutively as well until the translation was complete. So this allowed translations to work a lot better, because instead of having this one vector of understanding that had to like somehow capture the entire source document and pass that into the encoder slash writer to generate a full translation off of just this one vector of understanding, it's kind of like you could start the translation and produce new vectors of understanding that were contextualized by where you were at in the translation process. And this removed a big information bottleneck and allowed translation to work over longer documents. So that in of itself was very cool. And then in 2017, researchers at Google noticed that this concept of paying attention to stuff was actually useful outside of the context of translation. So let's revisit word embeddings for a second. Word embeddings are numerical representations of individual tokens that convey deeper meaning. But their meaning is fixed. Whatever you learned when you were training Word2Vec or whatever you did, that's it. It's like the meaning of the word is sort of fixed. But when you think about it, no word's meaning is fully understood until you've considered all of the company that it keeps in the words before it and potentially after it. So let's look at this kind of funky sentence here. I'm going to catch a fish at the bank. Now, if we think about the embedding for the word bank, it might make you think of checking accounts and your balance and that kind of stuff. Its meaning is only fully understood when contextualized by the other tokens in the sequence as well. And so this had been a long-standing problem, but the concept of attention that was developed in translation morphed into this concept called self-attention, where sort of we in some sense, to embed any given token, we would go look at all the other tokens in the sequence and figure out which ones are most important to contextualizing the meaning of bank, and we'd pay attention to all of them together. So we took this concept of attention that really helped translation systems get better, and we applied it just on one text as a way to read that one text even better, where each token in the text now was contextualized by all the other tokens in the text, and that was self-attention. And so self-attention, sorry to break the news, but self-attention in some sense maybe replaced RNNs as the preeminent best way to get to deeply read and understand text. RNNs still have a lot of uses and some nice properties, but self-attention largely supplanted them. And this overall architecture the original transformer architecture was a translation architecture that you would, when you're generating the output document, you would pay attention to the source document, but also the way you read the source document used self-attention, and the way you understood what you had written so far also used self-attention. Those things all combined were the transformer translation architecture, which radically outperformed previous stuff. And as we'll see here soon, even some non-translation architectures now get the transformer moniker, and it's mainly because they're using this concept of self-attention. So summing it all up, transformers allowed us, it removed several information bottlenecks. For one, every token could now be understood in the context of the other tokens, the company that it kept. And self-attention helped us pay attention to the right other tokens in the sentence. Like in this case, probably paying attention to fish really helps contextualize the meaning of bank. And the other thing transformers did was they allowed us to process much longer sequences of text, because we don't have to capture our entire understanding of that text into one vector. We can go back and reread as necessary. And so there was a famous paper about this concept called "Attention is All You Need." And so here's a picture of sort of what it looks like, harkening all the way back to part one. Let's say we have this input text, I have to read these books, and we put it through some tokenization scheme. Great, so now it's split up into discrete pieces. Then we put it through an encoding scheme that's just assigning a unique number identifier to each token. And then maybe we still do token embeddings, uncontextualized embeddings that are only a function of the token that you're looking up. So get the embedding for token 3, the embedding for token 24, etc. But then you're going to start to do these things called self-attention vectors, where it would actually be the self-attention of the embedding of 3. But I have some pseudocode here for those of you who can put up with that. But imagine that self-attention basically says, okay, if you want to get the self-attention understanding of token T, then get T's embedding and get the embedding for all the other tokens in the sequence, and then use this attention mechanism that the model learns during training that's going to help you pay attention to which other tokens in the sequence most contextualize T, and then output a new vector representation of the meaning of T that is not just a function of itself, but of all the other tokens around it, which is, probably much closer to how humans do it. And so you'd have this layer of self-attention. And now these LLMs, the first L is large. They are very large, and they would repeat this process many times. You'd stack self-attention layers on top of each other. GPT-1 did it 12 times. It's only gotten bigger since then. And by stacking multiple layers of self-attention enables the model to continually perform higher and higher level reasoning skills. Lots of hand waving there, but I think it's an accurate picture you can kind of take with you when you're thinking about these things. So that's sort of what self-attention looks like. And that brings me to the end of this content. And so in the next video, which is the last video, we're going to kind of talk about what else had to happen after transformers to get us all the way to the level of intelligence that we're seeing from LLMs today, like ChatGPT. There was a few more steps left, so I hope you'll join me for that one. Thanks again. Bye.